Hi everyone, my name's Kavya and I'm here to teach you a little bit about the basics of bioreactor modeling. So with this lecture, I hope you will be able to understand enough about bioreactor modeling to feel comfortable exploring it further because there's really so much to this topic that nobody could possibly condense it into a lecture under 2 hours. Um, so yeah, just to give you a little bit of introduction, on myself, I equally enjoyed math, chemistry, and biology in high school, and I wanted to study something that combined all three of these disciplines. And that's how I got drawn to biochemical engineering and studied that in undergrad at UC Berkeley. During undergrad, I spent 2.5 years doing molecular biology research on microorganisms like E. coli, and then also on this funky anaerobic sulfate reducing bacterium that's found in like desert soil crusts and in aquatic organism in aquatic environments called Desulfovibrio vulgaris. During the summers, I did internships at Merck working on various aspects of vaccine production, from operations to process research and development. After undergrad, I spent 3 years working as a fermentation process engineer at Bold Threads, which is a biotech startup in the San Francisco Bay Area that makes novel biomaterials like spider silk straight from sugar using yeast. If you'd like to talk about any of this or have any questions about any of this um, type of work or about pursuing a career in biotech, feel free to reach out to me over email or Twitter, and I'll be happy to share with you whatever I do know. So, I wanted to start off by giving you guys a brief introduction on fermentation and how it has already impacted our lives. Fermentation processes have been used by humans for thousands of years to make products that we consume in our daily lives. The most, the most well known examples are using yeast to make beer from barley or wine from grapes. However, a lot of foods we consume are also made by fermentation, such as kimchi, yogurt, soy sauce, and tofu, just to name a few. Now, some of you might have seen the word fermentation exclusively used in biology courses to describe what happens when there is no oxygen in your growth medium, so your cells do not respire and instead they ferment and make ethanol. However, in terms of biochemical production, the term fermentation is used broadly to describe a process where microbes are used to produce any desirable product under any conditions. And I hope that this clears up some confusion that you might have had moving forward through this lecture. So, with the engineering of microbes, yeast and E. coli, we can actually use fermentation as a means of producing a variety of chemical products that are normally derived from petroleum, such as styrene and lactic acid, and not just food products. This is a more sustainable way of producing these chemicals as it doesn't rely on fossil fuels and is a cleaner process. And yeah, so in general, fermentation processes are more clean than traditional chemical production processes. The engineered microbe, which is prepared using the techniques that you learned in the wet lab section of this series, such as CRISPR, acts as a biocatalyst. A biocatalyst is a living organism that speeds up a chemical reaction. In this case, the overall chemical reaction that needs to be sped up is the reaction that converts the feedstock, for example, glucose, into a chemical product such as styrene or lactic acid. However, each microbe contains a complex network of thousands of reactions that have been evolved to help the microbes divide. Therefore, you have more biomass produced in addition to your target chemical product. You also have byproducts made in addition to your target chemical, and these are typically metabolites that the microbe needs to survive and grow, such as acetate and ethanol. So even though you just want your feedstock to be converted to your chemical product, in reality, your feedstock also goes towards making more biomass and other byproducts as well. And so it's not a perfect conversion. During fermentation, feedstock, water, and salts and the engineered microbe are added in different ways to a bioreactor. Um, the salts that are added are those needed by the microbe to grow and survive, like calcium, potassium, magnesium, and trace metals. And trace metals are a mix of salts needed in very small quantities for microbial growth. This bioreactor equipment provides the ideal conditions for the microbe to be able to make to grow and make the product of your choosing. So it provides oxygen if needed. It provides cooling and mixing and it also provides cooling and mixing. In the end, you're left with your product mixed in with byproducts and more microbial biomass. You would then recover and separate your product from the rest of the cell culture. And while we won't go into that aspect of biochemical production here in this lecture series, it's definitely something you should think about when designing your IGEM manufacturing project. You should also think about which microbe to use for making your product, as different microbes are inherently good at making different types of products. I want to spend a little bit of time talking about feedstocks. There are various different feedstocks that can be used for biochemical production. I won't have time to cover all of them in this lecture, but I'd still like to introduce you to the idea of thinking about feedstock selection. So, feedstocks can either be sugars like xylose and glucose, or compounds derived from sugars like glycerol and or ethylene glycol. These can be fed to the microbe directly. They can also be the things that contain sugars that are pre-treated to release their sugars before being fed to the microbe, such as lignocellulosic biomass, which is the woody part of plants, corn, and molasses. Sugars are used in most feedstocks for fermentations, and out of all the sugars, glucose in particular is very commonly used. Some fermentations are used can use even use mixed feedstocks. One thing I want to emphasize is that more feedstocks exist than are depicted on the slide, and there are even more potential feedstocks that are being researched. There are scientific and non-scientific factors that affect feedstock selection. From a scientific standpoint, selecting a feedstock that will get better performance out of the pathway needed to produce the target chemical and one that is easily utilized by the host microbe is advantageous. From a non-scientific standpoint, the cost and availability of the feedstock are important to think about. How expensive is it? Is it available nearby? Also, there's the whole fuel versus food debate surrounding corn and molasses. Here, lignocellulosic biomass is good because it's not food, but bad because you need pre-treatment to break it down into sugar for scalable fermentation processes. Because you can't, it's impossible for the cells to use to break for most cells to break down lignocellulosic biomass on their own. So there's really no right answer here, but there are good ways to think about this to make sure you can back up whatever choice you do make. So right now I just want to go into the equipment that comprises a bioreactor and how it's set up. So first you have a vessel, which is typically a glass or a stainless steel vessel that holds the cell culture. You have a thermal element that varies from reactor to reactor that can remove and provide heat based off of what your process needs are at a given time. You have a condenser that can prevent evaporation. You have a stirrer and an agitator, and the agitator is powered by a motor that fits around the agitator shaft to mix the culture. You have a sparger that delivers gaseous substrates to the reactor. These can be oxygen, carbon dioxide, or nitrogen, depending on what your process needs. You have probes to measure pH, temperature, and dissolved oxygen levels and in real time. And you also have a control tower that controls actuators, which are physical elements that maintain temperature, pH, and dissolved oxygen levels. Finally, you have a computer loaded with control and visualization software that you can use to set up feedback control loops and visualize real-time parameters like temperature and pH. And one thing that I wanted to emphasize is that with this equipment and setup, there's so much that you can model over here. And for the rest of this lecture series, I'll be focusing on the type of modeling that will be the most useful for economics. But depending on your purpose and needs and how much time you're willing to spend on the modeling, you can model other things too, like fluid dynamics responsible for the heat and mass transfer of culture components, for example. Another thing I wanted to emphasize is that mixing is really important to maintain temperature and pH through heat transfer and mass transfer. And it's also really important to deliver oxygen and feedstock to the cells. So if you have a problem with your mixing, if your motor, agitator, and stirrer system just isn't working, you will lose your fermentation run, for example. So I wanted to talk a little bit about the different types of bioreactors, which vary by how components are added to the reactor. So first up, you have a batch reactor, which is very simple. It has all the components, the cells, the growth medium, and the carbon source in the reactor itself, and you have no inlet feeds or outlet streams. It's very commonly used for bioprocessing, and it's very versatile because it's so simple. You also have another type of reactor called a fed batch reactor, and the fed batch reactor contains the cells, the growth medium, and a starting amount of carbon source in the reactor initially, and then more carbon source in addition and additional nutrients are added via an inlet feed throughout the fermentation run. And fed batch reactors are used in situations where it's advantageous to keep carbon source concentration low so you avoid overfeeding. And you so you typically only feed as much as the cells can consume without overfeeding at a given point in time. And this keeps the cells hungry and able to consume more feedstock over the course of the fermentation. Therefore, fed batch processes can make more product than batch processes. Finally, you have a chemostat, which where you start off with just growth medium in the reactor, and then you have an inlet feed with carbon source and cells, and an outlet stream with carbon source, cells, and product. Once steady state is reached, you will have the inside of the chemostat look like the outlet stream, and you also have the inlet and the outlet volumetric flow rates equal in this situation. Chemostats are used to generate a large amount of product, and they're used to also generate when steady state data about an organism for a metabolic model, which is basically a model about all the reactions that we know that happen within the organism. So right now I want to talk a little bit about the different phases of cell growth in a batch reactor. So what you see over here applies to to most microorganisms that grow in a batch reactor. Uh, the growth starts off with a lag phase where the cells are just getting where the cells are kind of just getting acclimated to the new environment, and is followed by an exponential phase where the cells are growing and dividing rapidly, and then a declining growth phase where the cells are starting to use up, where all the nutrients in the environment are starting to get depleted, and that is and that results in a slowed down cell growth. And then you have stationary phase where all cell growth stops, and all resources are diverted to just the maintenance of the cells that are still living. And then after the stationary phase is when you have cell death, where the nutrients in the environment are not enough to sustain all the living cells in the population at that point in time. And and just to kind of note, this holds true for any closed system containing cells, growth medium, and nutrients. So this could just even be a test tube, and it doesn't have to be a bioreactor with all the equipment that you saw in the previous slides. And yeah, as you might have deduced, the y-axis is a proxy for a cell number. So it's just in this case, it's the log of the cell number. Although it could also be in other graphs, it could also be cell density, for example. And then the x-axis is time, and this figure is from a textbook written by Blanch and Clark, which you will see in more detail later on in the lecture series. And the reason why I wanted to show you guys this is because when you are running a fermentation in a bioreactor, it's really up to you when you decide to stop the fermentation. And usually you don't want to spend precious bioreactor time that you somehow, in some way, shape, or form, pay for with when your cells are in the death phase, or sometimes even in the stationary phase. Like, that's not doing you much good. So where you want to end your fermentation is definitely before the death phase. And then it depends, if your product is something that's produced only while cells are growing, then you want to end your fermentation over here right before stationary phase is reached. If your product is something that you don't have to have cell growth to be able to produce a product, you can go a little bit into stationary phase to make sure you get the maximum amount of biomass um, in your uh, in your reactor before you produce your product. And so, and also, if you want to transfer cells from one culture to another culture so that they can enter the second culture with minimal lag phase, you want to harvest them mid exponential phase, so you're sure that they're rapidly growing when they end up in the newer culture. So I want to take you guys through this little case study next to see if you can connect any of the to give you guys just practice with connecting what you've learned so far to a real world application. So in this case study, you have a situation where a large brewery that sells a batch of yeast to a microbrewery that currently works for them at scale. However, this batch of yeast obviously is not the same exact cells that the larger brewery uses. It's just from the same batch. However, the microbrewery is unable to get the same batch of yeast to grow. However, the microbrewery can get other strains to grow under their fermentation process. So it's just particularly with this batch of yeast. What could be the problem? So just pause this video and take some time to think about it or discuss in your groups if you're watching this video as a group. Okay, so I would have loved to have done this in person for initially, just because when we planned these case studies, I was so excited to hear what you guys came up with. Where I'm trying to go with this is in this situation, it doesn't seem to be that there's anything wrong with the process. So it has nothing to do with the equipment. It's working fine. It looks like that's not the issue over here. My concern is with the batch of yeast. And as I kind of alluded to in the previous slide, when you harvest yeast to be inoculated into a new fermentation process or a new bioreactor is very important. And it's possible that the large brewery just did not harvest them during mid-exponential phase, like would be best practices. They might have harvested them too late, or maybe even after cell death had occurred. So maybe the batch of yeast that the microbrewery got was not a viable version of the batch that was working so well for the large brewery. So that's where I was trying to go with this, the way this problem was set up. So how do we mathematically model bioreactors? You kind of use the general idea, a general concept that we learned in chemical engineering, or even like before that, even physics, that mass and energy can neither be created nor destroyed. So what goes in must come out. And this kind of leads to two principles: the conservation of mass, and the second principle, the conservation of energy. And both of these principles can be generalized by can be like, for both of these principles that we can apply the general balance equation. So, and the general balance equation is that any change is equal to what goes in minus what comes out plus what's generated minus what's consumed. And you'll be able to see this in most of the equations that I am about to go through. And if you want to learn more about any of these equations and where they come from, look up the textbook that I'm taking all of this stuff from, which is the Blanch and Clark Biochemical Engineering textbook, published in '97. Now let's take a look at the general mass balance equation for a batch reactor. This assumes that the culture medium is well mixed so that mass transfer effects have minimal limitations, or negligible limitations, I should say. This is a mass balance equation for the chemical I, with the mass being represented in terms of concentration. And so the term that represents the concentration of I is C sub I, and the units are in moles per liter.
Other terms that are important are capital V, which is the reaction volume in liters, and then C sub J, which is the concentration of species J in moles per liter. And the pointer here, yes, so the R term, and the reason why we have C sub J is that the R term for the I species can be a function of the concentrations of different species, such as the J species. And if you want to learn more about why this could be the case, you'd have to learn more about kinetic rate laws and reaction kinetics, and you can uh, learn a little bit about that in the textbook if you are interested. Um, so the next thing that we would do is we're going to make the assumption that the volume of the culture stays constant, and this allows us to treat the volume term as a constant. So we can cancel it from both sides of the first equation um, to get the simplified mass balance equation, which states that the change in concentration of I is the rate at which it is either produced or consumed um, in the in the cell culture. And the simplified mass balance equation is important because the mass balances for cell growth, substrate consumption, and product formation are derived from this general equation. So the Monod model is one type of model that describes equations for cell density, substrate, and product concentrations in a batch reactor, and goes without saying that these are all mass balance equations. Um, so the Monod model was developed by Jacques Monod in the 1950s, and it is based off of E. coli growth at various glucose concentrations. And the assumptions that underlie this model are that one of the assumptions built into this model is that only one substrate, which is the growth limiting substrate S, is important in determining the rate of cell growth. And the Monod model for cell growth looks very similar to the Michaelis-Menten model for enzyme kinetics and gas adsorption models. So if this isotherm-like shape looks familiar to you, it's because it is familiar. So the terms that are important in this model are mu max, which is the maximum specific growth rate of the organism on the specific substrate S. K sub S is the concentration of S at which the growth rate is equal to half of mu max. And just to mention, I think I forgot to mention that max are inverse hours. We also have Y sub S, which is the yield of cells on substrate S, and the units are grams of cells per gram of substrate S. And the cell density and substrate equations look as follows, and you can sort of see how the Y sub S term factors into the ds by dt equation. The yield of cells on substrate determines how quickly the substrate is consumed for cell growth. And you can actually experimentally determine the specific growth rate at different substrate concentrations and plot it versus the concentration of S, as you can see in this graph, which is found in the Blanch and Clark textbook. And you can actually infer mu max and K sub S from this graph. So like mu max is about 0.5, so half of mu max is about 0.25. And then if you look at K sub S at half of mu max, if you look at the concentration of S at half of mu max, it's about 0.5 grams per liter, so that's what K sub S is. So defining a product equation under the Monod model is tricky because it really depends on how the product is made. So let's consider a case study where the product is made that is both growth associated and non-growth associated. So the cell density equation in this case is the same as what we saw before. The product concentration mass balance equation dp by dt is equal to, it has a growth associated term, which is proportional to cell growth, the rate of cell growth via a constant alpha, and it also has a non-growth associated term, which is proportional to cell density at a certain time via a constant beta. And in terms of the terms and constants that we have for this case study, you have mu max K sub S and Y X sub S at as before, but then you also have the yield of product on substrate S, which is YP sub S, and the units are in terms of grams per product per grams of substrate S. And as a result, you can see dS by dt has two quote unquote consumption terms. One to show you how much of the substrate is being consumed for biomass production, and the other to show you how much substrate is being consumed for product production. And once you substitute the equations for dx by dt and dp by dt in the ds by dt equation. So what you're doing is you're taking this, substituting it here, and then this whole thing, and then substituting it here. You have an expression for ds by dt that depends on all known constants that you could, and so you can model it computationally. And just to kind of reemphasize, y x sub s and yp sub s are terms that you can model or measure experimentally in the lab, and you can also measure alpha and beta in the lab. So now I'm going to kind of expand on the idea that the Monod model can be modified for many cases, and these cases can even be for a cell culture happening in different types of reactors, like the fed batch reactor and the chemostat reactor that we saw before. And the textbook has many more examples of this. However, for this particular case study that I'm going to go over in depth in this lecture is a case study where you have competitive inhibition of growth by the substrate in a batch reactor. So a simplified way of thinking about this is that when the substrate is present in high concentrations, it cannot bind to the enzymes required for cell growth. Thus, the growth reaction can't proceed. We're going to define a new term, K sub I, which is the concentration of S at which inhibition is half the maximum inhibition. And it tells you how potent the substrate inhibition is. So the change in cell density mass balance equation dx by dt now incorporates the K sub I term, as you can see over here. The equation for ds by dt for this case is not displayed here because it's not very intuitive. It involves dimensionless variables, and it's a little bit complicated to kind of explain how it's derived, but it's in the textbook, the Blanch and Clark textbook, if you're interested in learning more. So, and once you solve for S and X, as usual, you can plot S and X versus time for different K sub I values, as you can see in this figure here. And as you can see, in general, at the beginning of the culture, you have slow growth at high substrate levels, and then as the substrate is consumed and inhibitory effects are reduced, the growth becomes faster and faster. So you kind of like have a lag phase and then an exponential phase, and you might think that this looks very just, similar to a regular cell growth curve, and you're probably right, but where you can really see the inhibitory effects is that when you look at different K sub I's. A lower K sub I is means there's stronger inhibition, and there's a slower substrate consumption at the beginning, and so a longer lag phase for cell growth. And so you can really see the it's hard to tell that for the K sub I is equal to one case. It's hard to tell by looking at it that it's there's inhibition, but then if you plotted it against a situation where you had no inhibition, then you would be able to tell the difference. But you can clearly tell the difference when you compare two different K sub I's. So let's look at the energy balance equation for a batch reactor. This equation, energy change within the system depends on the heat generated by the system, the heat removed from the heat generated by the system, and this is by the cells that are growing, the heat removed from the system by the cooling jacket or the temperature control unit around the vessel, and then the work done on the system by the agitator stirrer system, or the airflow itself if you're talking about a bubble column. So what do these terms mean? Rho is the density of cell culture in grams per liter. Capital V is the culture volume in liters. C sub P is the specific heat capacity in terms of, and the units are joules per gram Kelvin. Capital T is the temperature in terms of Kelvin. Delta H sub R is the heat generated by the fermentation reaction in joules, and it's positive in this context. R sub X is the volumetric rate of increase of dry cell weight in grams per liter per second. Capital Q is the heat flow from the reactor associated with the temperature control in joules per second. And finally, W sub S is the generation of heat by agitation in joules per second, which is also positive in this context. So I want you guys to pay attention to the sign convention here for a second. Why do you think the Q term has a positive sign? How do you think the signage of Q changes over the course of a fermentation? So before the exponential phase, what you would need to do is you would need to add heat to maintain optimal temperature, because optimal temperature is usually somewhere around 37 degrees, which is fairly warm, warmer than room temperature, and the cells are not growing fast enough to provide enough heat to heat your reactor up to that point. So the overall change needs to be, positive. And when you're during the exponential phase, you would need to remove heat to maintain optimal temperature. So before the exponential phase, the Q term would have so based on the sign conventions in this equation, before the exponential phase, the plus Q term should be a negative number, because when work is being done on the system, as you can see from H sub R and W sub S, you would need this to be a negative value. And then during the exponential phase, you would need to remove heat to maintain optimal temperature. So the plus Q subterm would need to be a positive value. So Q would be a positive value. And so just like the final thing that I wanted to say is that the temperature profile, i.e. temperature versus time, is a user input and is known. And it's sort of like, well, the temperature profile itself isn't known, but the temperature set point that you want for your run is something you can program into the equipment, and this equation will tell you how much energy is needed to maintain that set point. So I want to go through a case study, an extension of the first case study with you guys. So the microbrewery has fixed the problem of their yeast not growing. Now the most pressing challenge is that they are losing money on their new beer product. Their products are selling out consistently, and waiting lists are significantly long, and their staff is working to 100% capacity. Yet somehow their profits are still in the negative. How can they improve their profits? So yeah, I'd like you to pause this video and just take a couple of minutes to think about it. So where I was sort of trying to go with this is to try to get you to think about the economics of this, to think about bioprocess economics from like a more real life scenario, before I kind of like build on some of the concepts that are needed to describe it. So I basically, like, where I was trying to go with this is that you can see from the case study that demand is not a problem. And if any of you've taken economics classes, that you've seen the supply and demand curve, like, we know that demand is not a problem here, but they're still not making any money. So one of the most obvious things that you could do is increase the price of your product so you can make more money. And like, you might be tempted to think about, improving the efficiency of the process, but as you can see from this case study, doesn't seem to be a problem here. So that's where I was sort of trying to go with this. So what's the connection between the mass and energy balances that we just saw and bioprocess economics? So each of these equations kind of tells you something that you need to know for for bioprocess economics. So the cell density equation tells you how much biomass is made, and biomass in terms of economics is a waste product that takes expensive substrate away from your product. The substrate concentration equation tells you how much substrate is consumed, and substrate is a raw material that you pay for. So that's why you need to care about it. Product concentration, the product concentration equation tells you how much product is made, and product is something that you sell for revenue. The energy balance equation tells you how much energy you need, and you care about energy because it's a utility that you pay for. And one thing that I wanted to point out is that when you design your own bioprocesses, you can save money by recycling the used biomass back into the bioreactor. So, what metrics are you typically used to measure the performance of a bioreactor run? Um, I just wanted to take you through all these different metrics so you can kind of use them in terms of your in your to measure, both the performance of your manufacturing project and also kind of feed into bioprocess economics. So titer is the concentration of product in cell culture in terms of grams per liter. The yield is the grams of product produced per grams of substrate in terms of grams of product per gram of substrate. Your productivity is the grams of product produced per unit volume of cell culture per unit time, so grams per liters per hour. And a high productivity means that you need less reactor volume to make the same amount of product, and this usually ends up saving you money. Specific productivity is the grams of product produced per gram dry weight of cells per unit time, and the units are grams per gram dry weight per hour. And specific substrate uptake rate is the grams of substrate consumed per grams dry weight of cells per unit time. So also just grams of substrate per grams dry weight per hour. And it tells you, the last two just tell you how hard each cell is working. So a cell that's working hard in your bioprocess is consuming substrate and making product. So this is a good segue into the bioprocess economics section of the lecture, and bioprocess economics helps you answer the questions of how you should price your chemical and what application you should target. A good resource for bioprocess economics is the textbook by Turton et al. Shown here, and if you want to learn more about this topic in depth, that's a good resource.
So, how do we decide if a bioprocess is economically feasible? There are four major components that go into helping us decide this. So, the first is figuring out capital expenditure. This figuring out CapEx, you to do that, you basically have to answer for yourself. How much money does it take to build a new chemical plant? Um, for figuring out manufacturing costs, which you might have also heard of as operational expenditure or OpEx, you would need to answer the question of how much money does it take to operate a new chemical plant. So CapEx is build, manufacture, or OpEx is operate. Um, Engineering economic analysis helps you is where you answer the question of, does this process make money, and does it make more money than processes that do the same thing? And a key concept of engineering economic analysis is the time value of money, which we will talk about more later on in this lecture. And finally, there's profitability analysis. Will a specific project be profitable? And this can be applied to anything between a small process improvement project or a large multi-million-dollar venture to build a plant for a new product. And I'd say kind of I wanted to point out is that engineering economic analyses has like a lot of techniques that are further detailed in the textbook that we won't have time to go through today, but you would essentially use these techniques that you learn in engineering economic analysis and then apply them to profitability analysis. So there's like a lot of overlap between these two sections.
So I wanted to introduce the concept of a process flow diagram, which will kind of which is necessary for any type of engineering economic analysis. This involves drawing out in detail what goes into each process stage, i.e. inputs, and then what comes out. For example, outputs. On the left, we have a schematic process flow diagram, or a PFD, for a bioreactor, which is the unit operation we've seen in detail in this workshop. So what you have is going in is feedstock, cells, media component 1 to media component N, whatever that is, and then the substrate, I guess, would be the feedstock, but the media components are just whatever would go in your medium. And then what comes out is your product, your biomass, which, I guess depending on your process, it's either recycle or waste, other waste, and then your byproduct. And then on the right is an example of a more complete process that I found in the textbook. So you can see that it contains unit operations that happen before and after the bioreactor step. So the steps that happen before are the unit operations, the filtration of the media nutrients, and the filtration of the air that goes, or I guess like the splitting up of the air into oxygen and other things that go into the bioreactor. And what comes after are all the filtration steps needed to separate your product from the cell culture, so you get the purified and concentrated product. And the reason that I have this here is that I wanted to emphasize that for a thorough economic analysis, you'll need to focus on your whole process from start to finish and not just the bioreactor. So on this slide, I'm going to talk a little bit about how you would go about figuring out CapEx for your plant. So what you would do is you would size and price every piece of equipment in your process flow diagram, and then every piece of equipment needed to start up and shut down, each piece of equipment in your process, and then your process overall. So for the example of the have to consider would be the size. So it depends. If you want to, for just testing out your process, you would use a pilot scale range of 300 liters to 1,000 liters. For producing your actual product, you would need a production scale. So anything in the range of 2,000 liters to 500,000 liters. The construction material is typically stainless steel for bioreactors, and that's something that you would have to consider to figure out how expensive your bioreactor is. And then you would also have to price out supplementary equipment. So, for example, for bioreactors, this would be a clean in place skid, which is basically equipment that's required to clean the bioreactor after a fermentation run. And there's also this would also include a sterilize in place skid, which is basically equipment that's required to sterilize the bioreactor before you start a new bioprocess or a new fermentation run in that bioreactor. And feeding all of this information into correlations will give you a good estimate of the price of this reactor. However, if you want a really accurate estimate, you would need to contact vendors for a quote that is, and this is typically done in like the next phase of costing out a project, not the initial phase. And for more information on when this is done and what these correlations look like, please refer to the textbook. One thing that I wanted to note is that renting out a manufacturing facility versus building one eliminates this upfront cost. So the facility rental becomes an operational cost, and your CapEx is kind of all but eliminated. You would just need to buy the capital that the facility that you're renting out doesn't have that you need for your process. And this is becoming more and more common, especially as more startups get into the bioeconomy industry or the biotech industry, because you're, as like a new company, you're not going to have hundreds of millions of dollars to build a plant just to make your product. You would need to make your product, show that it sells, and then if it's successful, you get to build a facility around it. So that's one thing that I wanted to emphasize. So moving on to operational expenditure, or OpEx, you would basically figure that out by figuring out for each step in your process all the costs associated with running the process. There are two major subcategories for OpEx costs. So there's direct costs, which vary with the rate of production. So these the more units you produce, the more your direct costs will be. And then there are fixed costs that do not vary with the rate of production at all. And these are just depreciation of your equipment and then the taxes that you need to operate your business in a certain location. Um, examples of some examples of direct costs include salt, feedstock, and biomass, which are raw materials, the deactivation of the spent cell culture coming out of the bioreactors, which is basically waste treatment, operating personnel and supervisor wages and salary are included as labor costs. Utilities are also included, and utilities cover a lot in terms of electricity that is needed for the mixing for mixing the bioreactor and for operating the whole system that runs the bioreactor. You need cooling water, which is needed to cool the bioreactor. There's steam that's needed to sterilize the bioreactor. There's inlet gas, which, like for example, air and nitrogen, which is needed to provide aerobic or anaerobic conditions to the bioreactor, depending on your process. And certain laboratory charges would count as operating or direct operating costs, such as those required for product, cell, and substrate measurements throughout the fermentation run, quality control, and troubleshooting laboratory charges. Yeah, so for a complete list of OpEx related or manufacturing costs, refer to the textbook. There's a lot there. And then it also gives you pretty good ways of estimating labor, utilities, and raw material costs. Yeah, so I would refer you to the textbook for more information about this. So now I'm just going to talk a little bit about engineering economic analysis, i.e., does a process make money, and how would you kind of go about figuring that out? So the answer is that there are a lot of complex techniques that are covered in, or not, well, not complex, but a lot of different techniques that are covered in. They're pretty simple, but they do take some uh, it does take spending some time understanding them and practicing them with different examples to be able to get the hang of them. And they're covered in detail in the textbook, and they can. So I'm going to refer you to the textbook if you really want to practice with these techniques. But they. I just kind of like wanted to drive home some key points in this lecture series about like what engineering economic analysis does for your what it can help you do as a tool. So on the left-hand side, there's a figure that shows the typical financing scheme for a chemical plant. And as you can see, there's like many different layers. The bank invests money into a company, and the company invests money into a project. And the project is supposed to take low-value chemicals and produce high value chemicals. And at every stage, the bank needs to generate profits, so it needs to get that money from the company. The company needs to generate profits, it needs to get that money from the project being profitable. So this entire scheme kind of depends on this aspect of the scheme working out or panning out. So what you need to take in is low value chemicals or raw materials, and then you need to produce chemicals that are expensive that will that sell for a high price. Because if you go from low value to low value, that while that may be really useful in theory, and it's definitely something that should be considered to do. It's definitely something that's worthwhile doing, but it does it fit within this scheme of economics? Like, is it that's something you would have to consider. So yeah, the a drive. So I guess like the key concepts that from the engineering economic analysis section of the textbook that I wanted to highlight were as follows. So the time value of money is something that's really useful for engineering economic analysis, and just for your own personal finance knowledge. So money plus time is equal to more money. So you might have heard the saying that $5 today is worth more than $5 tomorrow, or definitely more than $5 10 years from now. And a driving force behind the time value of money is that there's an interest rate. So upfront investment needs to be paid back in the future with interest. Also, the capital that you buy all that equipment depreciates over time. So by depreciates, I mean it loses value, monetary value, and that eats into your revenues. So however much profit you make, it kind of has to combat the depreciation as well. So let's talk a little bit about profitability analysis. So this answers the question of, will this process be profitable? As I mentioned before, this uses the techniques of engineering economic analysis to determine the profitability of a process. So, three major criteria for evaluating profitability are time, cash, and interest rate. So, for time, and yeah, so I'm just going to go through some example metrics for each of the following for each of the following categories, but there are more. There's more. The textbook contains more details on the type of metrics for these categories and which ones are recommended to be used for a more accurate analysis, and which ones are more accurate but also more time consuming. So, yeah, without further ado, an example metric for time is payback period. And this a payback period means it's basically the time required after startup to recover the fixed capital investment for the project. And just bear in mind, this is just the time that's needed to recover the capital investment. This doesn't have anything to do with all the other money that you spend on operating costs and whatnot. And I just also wanted to emphasize that just because it's not captured in this metric, it's also it's definitely, you do need to recoup those costs in order to be profitable. Cash is an example metric for cash is the cumulative cash position, and this is basically the worth of a project at the end of its life. So the sum of all positive cash flows and divided by the sum of all negative cash flows. Interest rate, an example of a metric for the interest rate is a return on investment. And that is the rate at which money is made from our fixed capital investment. And that is equal to the average annual net profit divided by the fixed capital investment. So it's basically how the rate at which your upfront capital investment is making money. So, just to kind of summarize all the things that I've kind of tried to say about economic models so far, and perhaps give you kind of like a concluding way to think about this for this lecture series, is that think of it as a budget proposal for your product. It will, and if you do present an economic model as part of your iGEM project, it will probably be judged as a list of priorities. And in general, for economic analyses, the more data that goes into the model and the more time spent developing the model, the more accurate it will be. And more complex models will require sometimes expensive software to solve. So keep this in mind as you manage your own expectations or set out or assign yourself work to do an economic analysis for your project if you choose to do so. And I'd like to show this figure that was generously given to us by Allison Simmons from Savant Technical Consulting, who presented this at a Biozone Techno-Economic workshop. And as you can see, it shows you how your actual process model, so the inputs, wastes, and products, interfaces with the economic analysis to kind of summarize what has been said. So the inputs from a list of inputs, you can figure out the cost of the inputs. And from your process model, you can figure out infrastructure, equipment, labor, and operating costs. From your products, you can figure out the waste disposal costs, and also on the flip side, the selling price of your products. And that is something that, and if you feed all of this into an economic analysis, it will tell you whether your process is profitable or not. So I hope this kind of summarizes that you need a well-defined process, and you need a well-defined process in order to have economic analysis that will tell you something useful or something sound or accurate. So just to kind of summarize, how are bioreactor modeling and process economics connected? The yield from the mass balance is used in cost models for price prediction, which gives you an estimate of the economic feasibility of the process. So and it's not just yield, as I said before, it's like a lot of different things, but it's just the yield is like one of the most important things that you can get from your mass balances. So yeah, that brings us to the end of this lecture series. I'd love to hear from you on whether you found this useful or not, and I'd love to hear from you if you have any questions about any of the material. If there's anything that was not explained clearly enough that you would like to learn more about, please feel free to reach out to me via email or Twitter. I'd like to acknowledge Patrick Diep, who is the program coordinator of CSberg, for giving me this wonderful opportunity, and the entire CSberg team for their support and lively and helpful discussions throughout this year. I'd also like to thank Emma Harrison, who's a master's student in my lab, the Laboratory for Systems Metabolic Engineering. And where I'm a second year PhD student. I think I forgot to say that in my introduction. And I'd also like to acknowledge Allison Simmons from Savant Technical Consulting for kindly offering us the use of her wonderful diagram. And the references from this slide deck that I think might be useful for you guys to look at, if you would like, are the two textbooks that I referred to throughout this lecture series. So the Blanch and Clark textbook, and then for biochemical engineering, and then the Turton textbook for analysis, synthesis, and design of chemical processes. And if you want to learn more about metabolic engineering and what goes on within the microbes and how to convert all those, think of those chemical reactions in terms of processes, the Kanjapur Lab Academy Metabolic Engineering Lecture Series on YouTube has some great content that I'm currently working through. So I think it might be really useful for you guys as well. So yeah, thank you so much for listening, and please feel free to reach out with any questions. Yeah, thank you again.